Alright, today we're starting a brand new big series. We're going to talk about quantum mechanics. Now, the internet is already packed with explanations of quantum mechanics. And the word quantum itself has kind of become what nano used to be years ago. Something you see slapped onto all kinds of products for marketing. These days, if someone says they don't know anything about quantum mechanics, it almost feels unusual. But most people only know a few headline ideas, things like quantum entanglement, quantum jumps, that sort of stuff. Here's what matters though. The early scientists, sure, they were better at math than us, but as human beings, they weren't fundamentally different. They didn't just wake up one morning and toss out a pile of brand new concepts for no reason, just to confuse ordinary people. Quantum mechanics became what it is today because people kept asking the most basic questions over and over, and the answers stubbornly refused to match our everyday intuition. Step by step, the theory got stranger and stranger. And the key point is, those weird phenomena at the beginning and the hypotheses people proposed to explain them, if you go back to the crime scene and think alongside the scientists who were there, it's actually completely understandable. So that's the goal of this series. We're going back to the scene. We'll try to understand, starting from scratch, what's so weird about quantum mechanics. And then we'll walk forward, step by step, all the way to the latest developments today. And don't worry, I'm not going to spend huge chunks of time on biography and historical storytelling, because we're not a history channel. Personally, when I read popular science books, I really don't like it when the author introduces a scientist and then feels like they have to start from what that person was like in elementary school, throwing in all kinds of field stories that have nothing to do with the science. In this series, when a scientist appears, we'll keep the personal details to a minimum. Their job is mostly to act as a thread, helping us follow the chain of questions. If you don't remember their names, that's totally fine. Also, since we're starting from the very roots, some of what we talk about might be things you've heard before. But to make this accessible for most people, we're not going to skip any of the crucial why questions. Quantum mechanics is a secret that the smartest human brains have been digging into for more than a century. It's not some harmless philosophical word game. It's about the deepest, most fundamental secrets of the world we live in. At the start, physicists were simply asking extremely basic questions. What is stuff made of, really? If atoms are the smallest units, why do different atoms have different chemical properties? Can atoms be broken down further? And what, exactly, is light? People had asked questions like these forever, but only about 100 years ago did we finally have the technology, the experiments, and the mathematics to seriously explore them. And once we did, physicists discovered that the microscopic world seems to follow rules that are frankly bizarre. And these strange behaviors aren't something physicists just made up. They're the result of experiments and logic. To explain why our everyday macroscopic world feels normal, you end up having to accept that the microscopic world is not normal. Or to put it differently, our normal world is supported by that microscopic abnormality. Some people, most famously Albert Einstein, suspected that underneath all this quantum weirdness, there must be an even deeper layer, a hidden master rule, the rule behind the rules. For decades, most physicists basically concluded that continuing to dig into the foundations of quantum mechanics was pointless. The theory worked. It did the job, so they focused on calculation and application. And during those years, physics absolutely exploded up into the sky, down into the earth, into everything you can imagine. People pinned down an enormous range of natural laws and used them to build cutting-edge technology. Quantum mechanics was treated as a tool for calculation, nothing more. Almost nobody insisted on asking the uncomfortable question, so what is reality, really? But starting around the 1960s and 70s, new ideas resurfaced. People proposed fresh hypotheses and reopened the hunt for that hidden master beneath quantum rules. New technology allowed physicists to design brilliantly precise experiments. And to this day, this remains a very active research field. And the deeper physicists went, the weirdness didn't fade. It got worse. So let's begin this journey into the deepest secrets of reality. Two small clouds that changed everything. At the end of the 19th century and the beginning of the 20th, A quiet revolution was brewing in science. This was the boundary line between classical physics and modern physics. Physicists like Newton and Galileo did incredible work, but their tools were limited, and their observations were more passive. By the late 1800s in Europe, physicists had much more precise instruments, more sophisticated experimental setups, and stronger mathematics. Differential equations, statistical physics, even non-Euclidean geometry, these tools were already mature. But physics at the time was still the continuation of the Newtonian era. It was still classical physics. Maxwell's electromagnetism had become deeply accepted. People knew atoms and molecules existed. Thermodynamics was well established. Theories felt elegant. Equations matched experiments beautifully. What physicists described back then was basically the same core physics you learn in high school today. And because of that success, many physicists stopped looking at the world with curiosity and awe. They started to believe that basically everything in nature could be explained by existing theory. Take light, for example. What is light? Where do colors come from? Maxwell's theory answered quickly. Light is an electromagnetic wave. Different colors are different wavelengths and frequencies. Light travels in straight lines, beams can cross, it carries energy. Newton had already shown that sunlight can be dispersed into different colors. Everything seemed under control, but in hindsight, we were still ignorant and a bit arrogant. It's almost as if fate chose a special moment right at the turn of the century. Lord Kelvin, one of the giants of thermodynamics, once argued that the building of physics was basically complete, that young physicists only needed to do a bit of minor patchwork. But, he said, on the clear horizon of physics, there were two small clouds that were unsettling, and both clouds involved light. Cloud number 1. Why does the speed of light appear the same in all directions? We know today that this line of questioning ultimately led Einstein to special relativity. Cloud number 2. Blackbody radiation. Now, blackbody might not mean what you imagine at first. A blackbody does glow. It's just that it doesn't reflect light from elsewhere. What you see is entirely its own emission. The sun, a red-hot piece of iron. These are all approximate blackbodies. A blackbody's light isn't reflected. It's produced by heat. That's thermal radiation. And physicists found something remarkable. The spectrum of blackbody radiation doesn't depend on what the object is made of. It depends only on temperature. In other words, just by looking at the color, you can estimate the temperature. Yellowish glow means lower temperature. Blue flames are hotter. Same idea. Given a temperature, physicists could measure the distribution of emitted light across frequencies and draw a very precise curve. And then the obvious question hit. Why does the curve look like that? What mathematical formula governs it? Physicists at the time strongly believed that beneath every law of nature, there must be a governing equation. That mindset, more than anything, was Newton's gift to physics. So if there's a curve, surely we can derive the formula. Thermodynamics and statistical physics were already advanced, so physicists assumed blackbody radiation came from vibrating electrons, producing electromagnetic waves. Fine, they thought. We'll just use statistical mechanics and derive the result. But physics failed hard. No classical theory could produce the correct spectrum, especially at high frequencies into the ultraviolet. Some theories even predicted that the energy emitted at those high frequencies should be infinite. That's obviously impossible. This disaster became known as the ultraviolet catastrophe. And this is where classical physics ends and quantum physics begins. Planck's desperate move and Einstein's bold meaning. In 1900, Max Planck faced the crisis, and he made a move that was, in a sense, brutally pragmatic. If physics can't solve it, then for now, forget the physical meaning. Let's build a mathematical formula that fits the curve first. Physicists love doing this. Observe a pattern. Write down a formula that matches it. Then manipulate the math until inside that math, you discover the deeper rule nature is hinting at. Planck, unbelievably, found a formula that fit perfectly. But physically, he couldn't justify it. He struggled for months and eventually realized something shocking. To derive his formula, one specific assumption had to be true. The energy emitted by those vibrating charges could not be continuous. It had to come in discrete packets. Planck proposed that the smallest unit of radiation energy depends on the light's frequency. That's the famous relation. E equals hf. Here, f is frequency, and h is a constant, Planck's constant. With this assumption, high-frequency radiation comes in large chunks of energy. Thermodynamics then tells you large energy chunks are less likely to appear. So you don't get endless high-frequency energy. No ultraviolet catastrophe. But remember, Planck's formula was first patched together mathematically. Planck himself didn't truly know what those energy packets meant physically. Because this idea didn't match any classical theory and didn't match human intuition at all. The person who gave it a clearer physical meaning was ironically Einstein, through the photoelectric effect. So what is the photoelectric effect? If you shine light on a metal surface, sometimes electrons are ejected from that surface. At first glance, that sounds simple enough. Light is an electromagnetic wave. It carries energy. So the wave gives energy to electrons, and they fly out. But the weird part is this. Whether electrons fly out doesn't depend on how bright the light is. It depends on the color, the frequency. It's like this. No matter how intense you make red light, it still can't knock electrons out. But with violet light, even if it's extremely dim, electrons can be ejected. Classical physics had no way to explain that. In Maxwell's theory, wave energy depends on intensity, not frequency. Frequency was just color. In 1905, Einstein published a major paper, often translated as On a Heuristic Viewpoint, concerning the production and transformation of light, explaining the photoelectric effect. Einstein said, "Electrons need high-frequency light to escape because light isn't a smooth, continuous wave of energy. It comes in packets, and each packet has energy. E equals hf. Higher frequency means each packet carries more energy. So a single high-frequency packet can deliver enough energy to knock an electron free. Lower frequency packets don't carry enough energy, no matter how many arrive. Because, in this picture, electrons aren't gradually saving up tiny bits of wave energy over time. Each interaction is like a hit from one packet. So a high-frequency photon is like a heavyweight boxer. Even if there aren't many punches, low-intensity one punch can still knock the electron out. Low-frequency photons are like a crowd of children. You can have as many as you want high intensity, but none of them can deliver a single punch strong enough. That's the idea. In a way, Einstein pushed Planck's concept one step further. Planck quantized the energy exchange of vibrating charges inside a hot object. Einstein said, "This isn't just about black bodies. If it's light, then its energy comes in packets." Einstein called these packets light quanta, what we now call photons. Each photon's energy is its frequency times Planck's constant. Using that, Einstein explained the photoelectric effect and got results that matched experiments extremely well. And that's when quantum officially walked onto the stage. So why don't we feel the world is quantized all the time? Einstein pointed out a simple reason. Planck's constant, h, is ridiculously small, about 6.626 times 10 to the power of negative 34 joule seconds. Blackbody radiation and the photoelectric effect were both phenomena classical physics couldn't explain. Planck first forced a mathematical model to match the data. Einstein then gave that model physical meaning. And that's how physics discovered the photon. Looking back today, compared to the deeper weirdness quantum mechanics will later unleash, this first step almost feels straightforward. But for people at the time, accepting the quantum idea was extremely hard. Planck himself struggled for years to accept the photon concept. Because light quanta didn't fit classical electromagnetism, Maxwell's equations didn't naturally produce energy packets. Planck may have thought he was solving a technical problem like a skilled craftsman. Find the defect, patch the equation, move on. But as the story unfolded, he realized he had opened a Pandora's box. And once the box is open, you don't get to close it. And here's the funniest twist. Einstein, the man who pushed photons into the spotlight, was not some lifelong cheerleader for quantum mechanics. In fact, Einstein spent much of his life opposing the deeper foundations of quantum theory. But that's a story for later. Atoms crack open, and classical pictures collapse. One of the deepest, most counterintuitive tensions here comes from an ancient question. Is matter infinitely divisible? By intuition back then, matter should be endlessly divisible. Molecules are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. So the next obvious question is, what are quarks and electrons made of? Modern physics, through the Standard Model, treats quarks and electrons as fundamental particles. They aren't made of smaller parts. In a sense, they're described by mathematical structures. And the question, how far can you divide matter, sits right at the beginning of quantum mechanics. By the late 19th century, scientists already knew matter was made of atoms, and they even classified them. Mendeleev built the periodic table and mapped chemical properties to different atoms. Classical physics was so successful that people weren't urgently demanding to know whether atoms had deeper internal structure. Then nature threw two problems at humanity. First, radioactivity. Scientists like Marie Curie and others discovered that uranium atoms could spontaneously emit radiation. Curie named the phenomenon radioactivity. This wasn't a chemical reaction between atoms. It was something happening inside the atom itself that strongly suggested atoms had internal structure we hadn't uncovered. Second, the electron. J.J. Thomson studied cathode rays and found a tiny particle that could be bent by electric and magnetic fields. He realized it carried negative charge, and he named it the electron. This was the first clear discovery that atoms contain smaller things. Atoms are overall electrically neutral, so if electrons are negative, there must be positive charge inside the atom as well. Thomson proposed a model we now call the plum pudding model. Imagine a positively charged pudding sphere with negatively charged plums embedded in it. The positive and negative charges balance. Heat the atom, and the electrons vibrate, radiate electromagnetic waves, and the atom glows. A neat picture, but it didn't survive. Thomson's student Ernest Rutherford, studying radioactivity, realized that radioactive decay is essentially an atom transforming into a different kind of atom. Something inside breaks apart and reorganizes. Some radioactive materials emit high-energy particles. Rutherford called one kind of them alpha particles. And alpha particles became incredibly useful, like bullets. In 1911, Rutherford performed the gold foil experiment. He fired alpha particles at a very thin sheet of gold. These alpha particles were energetic tiny bullets. Most of them passed straight through the foil as if nothing was there. Some were deflected, and a very tiny number were scattered backward almost as if they had bounced off something. Rutherford was shocked. How can something as thin as foil bounce a bullet back? There was only one possibility. The foil must contain extremely small, extremely hard, extremely dense objects. Rutherford concluded those objects were atomic nuclei. Most particles pass through because atoms are mostly empty space. A few are deflected because they pass near the nucleus. A very few bounce back because they hit the nucleus nearly head-on. From the scattering data, Rutherford estimated the nucleus is about 1/10,000th the size of the atom. He bombarded many materials and found that nuclei differ across atoms. Different amounts of positive charge, different masses. And this line of work led to the discovery of protons and neutrons. So Rutherford proposed the nuclear model, a tiny positively charged nucleus in the center, with negatively charged electrons around it like planets around a sun. But unfortunately, that model is still wrong. So wrong that many textbooks later stopped using that planetary cartoon. Because Rutherford's model has two huge problems. Problem 1. The nucleus is positive. Electrons are negative opposites attract. So why don't electrons spiral inward and crash into the nucleus? Rutherford initially said, because electrons orbit in circles, and centrifugal force balances attraction like planets orbiting. But that explanation fails. Why? Because an electron in circular motion is constantly changing the direction of its velocity. It's accelerating. And Maxwell's electrodynamics says accelerating charges radiate electromagnetic waves, losing energy. So the electron should radiate, lose energy, spiral inward, and fall into the nucleus. Calculations show it would collapse in about 10 to the power of -12 seconds. Planets don't fall into stars because they are essentially electrically neutral. Electromagnetic radiation isn't bleeding their orbital energy away like that. Problem 2. Atoms really do emit light, but each atom emits a very distinctive spectrum. It's not continuous. If you look up atomic spectra, you'll see that each element produces a set of discrete lines, some pattern that feels partly orderly, partly mysterious. And those spectral lines became one of our most powerful tools for determining the composition of distant stars. Someone eventually found a rule for hydrogen spectrum. A school teacher named Balmer wrote down a formula that matched the lines, but it was purely a fit, basically number matching. Nobody knew what it meant physically. We needed a physicist to give it meaning. Bohr quantizes the atom, and the word jump is born. In 1912, Niels Bohr stepped in someone who would become one of the central leaders of quantum theory. Bohr looked at Balmer's fitted formula and suddenly thought of what Planck and Einstein had done with quantization. So Bohr made a bold decision. Let's quantize the electron's motion inside the atom. Today, when we tell the story with Planck, Einstein, Bohr, it sounds almost natural, like Bohr was simply continuing the work. But at the time, this was not an obvious connection at all. First, nearly 10 years had passed. Second, Planck and Einstein were talking about light. Bohr was talking about atoms. Back then, nobody automatically assumed those were deeply connected. Here's how Bohr reasoned. He proposed 3 key ideas. First, electrons move in certain allowed orbits, and each orbit corresponds to a particular energy level. Second, when an electron stays in one of these allowed orbits, it does not radiate energy. Why doesn't it radiate? Bohr didn't really explain. He simply postulated it. But if you accept it, you're forced to admit the electron can't be behaving like a classical charge in a classical circular orbit, because that would radiate. Third, and most important, an atom emits or absorbs radiation only when an electron jumps between 2 different energy levels. The energy emitted equals the energy difference between the levels, and that emitted energy equals Planck's constant times the frequency of the light. Delta E equals hf. With these assumptions, Bohr's model perfectly explained Balmer's spectral formula and even predicted additional spectral lines that had not yet been observed. And if you look back at Einstein's photoelectric effect, a high-energy photon can knock out an electron. How much energy is needed? In Bohr's language, it matches the electron's energy structure, its binding energy in that state. Bohr's thinking had the same shape as Planck and Einstein's. Experiment forces a crisis fit the pattern, introduce quantization. But in quantum physics, this method immediately creates new puzzles. Why are there only a few fixed orbits? Why can't an electron exist between energy levels? Why does it suddenly not radiate while in orbit? What exactly is a jump? Why would an electron spontaneously jump from a higher level to a lower one? And if it jumps, what path does it take? Everything starts to feel deeply strange. Physicists began to realize the quantum world must have its own rules, rules that classical physics simply can't contain. Up to this point, experiments were dragging physics forward by force. Physicists had to accept facts they didn't like, then scramble to build models after the fact. That's not a great situation. Theoretical physicists needed to go on the offensive. And the first major theoretical battlefield was this: a massive contradiction between the wave nature and the particle nature of light. Waves, particles, and the double slit that refuses to behave. First, why were people so convinced light is a wave? The theoretical reason is simple. Maxwell's equations predict electromagnetic waves, and when you compute the speed of those waves, it matches the measured speed of light. So it was natural to conclude light is an electromagnetic wave. But theory alone isn't enough. You want direct experimental evidence. In the early 1800s, Thomas Young performed the famous double-slit experiment. This is something many people have seen in school. He used a candle as a light source, placed a barrier with 2 narrow slits, and put a screen behind it. Light passed through the 2 slits and formed a beautiful pattern on the screen, alternating bright and dark stripes, repeating again and again. If light were just streams of particles moving in straight lines like bullets, then you would not get stripes. You'd get two bright bands directly behind the two slits. But if you treat light as a wave, the stripes make sense. Think of water waves. A wave passes through two gaps and creates two wave sources. Each wave has crests and troughs. Where crest meets crest, or trough meets trough, you get reinforcement, bright bands. Where crest meets trough, you get cancellation, dark bands. This is interference. And based on wavelength and geometry, the bright and dark positions can be predicted precisely. Theory matched experiment extremely well. So people concluded fine light is obviously a wave. But blackbody radiation and the photoelectric effect were telling us, just as clearly, that light behaves like particles. So how can something be both a wave and a particle? How can a particle interfere? That question was still unresolved when a new problem arrived. De Broglie's bet and the moment matter started acting like waves. A young physicist named Louis de Broglie entered the story. As a doctoral student, he studied relativity, learned about light quanta, participated in photoelectric experiments, and also knew Bohr's atomic model was behaving strangely. He put these ideas together and asked a daring question. If light can behave like both wave and particle, could electrons, and maybe all matter, also have a wave side? So in his thesis, de Broglie proposed a striking formula. For electrons, protons, neutrons, any matter at all, the wavelength is equal to Planck's constant divided by momentum. In symbols, lambda equals h divided by p, and momentum p is mass times velocity. P equals mv. So, lambda equals h divided by mv. Don't worry if the formula feels abstract. What matters is the idea. De Broglie proposed a unified matter wave picture. Einstein later said de Broglie's insight might have lifted a corner of the curtain. At the time, the double-slit experiment wasn't precise enough to directly confirm this for electrons. Electrons are tiny. To see interference, the slit separation has to be comparable to the electron's wavelength, absurdly small. The technology wasn't there yet. So de Broglie thought of another approach: crystal diffraction. People already knew that X-rays scattered off crystals can form interference patterns. Because a crystal is made of atoms arranged in a regular lattice, it's like a perfectly repeating array of many slits. X-rays passing through that lattice interfere. De Broglie suggested that if a crystal's spacing is small enough, maybe it can diffract electrons the way it diffracts X-rays. In 1927, experiments succeeded. Electrons were fired at a crystal and produced a clear interference pattern. From the pattern, scientists could infer atomic spacing. They could also calculate the electron wavelength, and the match was stunning, essentially exact. So electrons really do behave like waves. De Broglie had pulled it off. Light and electrons weren't separate categories anymore. They were both part of a deeper wave-particle duality. But once you accept matter as both wave and particle, the next question hits immediately. What does that even mean? If an electron is a tiny point, how does it wave? If an electron is a spread-out wave cloud, why do we always detect it as a single point? And how does it go from a cloud to a point in an instant? We can't directly see electrons. We can only see what they do. So we go back to experiments. In the early 1960s, physicists finally performed true electron double-slit experiments. And they pushed it even further, sending electrons one at a time. And then the result got even weirder. Even if you fire just a single electron each time, if you repeat the experiment long enough and accumulate many detections, the interference pattern still gradually appears on the screen. But interference is supposed to come from two waves overlapping. So how can one single electron create an interference pattern? There's only one possibility. The electron somehow passes through both slits, at least in the wave description, and interferes with itself. And now, the wave here is clearly not like water waves rippling through space in the ordinary way we imagine. At this point, Pandora's box is truly open. And if physicists at the time felt confused, the even stranger quantum phenomena waiting ahead would make them nostalgic for this simple phase. Wrap up. So let's summarize today's story. Blackbody radiation was originally just a small cloud on the horizon of physics. But as physicists watched it drift closer, they realized it wasn't a small cloud at all. It was a massive storm, full of lightning. From this one small problem, we arrived at photons, electrons, and wave-particle duality. But this is not the finish line. It's the starting point of a much bigger mystery. We've discovered that electrons behave like waves. But what is an electron? Really? Why can't it interfere with itself? In quantum mechanics, one answer doesn't end the questions. It multiplies them. Physics entered a genuine crisis. But after crisis comes a new world. And the curtain on that new world has only been lifted just a tiny corner. The more exciting part of the story will continue next time.